The integral has an area interpretation, and that leads to a lot of fun facts about integration that are very useful when working with problems that involve integrals. So let me remind you what we're talking about here. We're going to talk about the integral from a to b of f of x dx. And I need to really reinforce this is the same thing as the integral from a to b of f of t dt. There is no x, there is no t. We're looking at every single thing between a and b. And so this is sometimes called a dummy variable because it's just a stand-in, like a dummy in bridge. But that's the way it goes. The picture is you look at the graph of f between those 2 points, and we go through this 4S process. And the steps are we subdivide. I guess I ought to write that down. Subdivide. So I'll just do a couple of subdivisions to give you the idea. So you subdivide the domain, and you have this little formula that we'll need later that says that the base, delta x, is a fraction. The top is b minus a over n. So here, n is 6, and so we've divided each delta x here is 1/6 of the whole distance. And so there's that. And then we sample. We take one value of the function in each interval, and I'll just draw a couple. So there's f sub 1, and there's f sub 4. Calculus books go through a lot of monkey motion about how to find the sample, but get the sample any way you can. That's not what integration is. Integration isn't all that monkey motion. It's the sample. And a lot of times we don't have any choice about what the sample is. We'll see that with trapezoid rule and Simpson's rule. And so anytime you have a passive function, that's the situation. Anyway, I've drawn a couple of samples, and there should be one in every subinterval, and the diagram would get too busy, so I left it out. Okay, so now we form the sum. The sum is f sub 1 times delta x plus f sub 2 times delta x, and the last one is f sub n times delta x. So that subscript, all these things are connected to the function f, so the letter f should appear, but they're all different, so we have to do something to make them different, so we throw in the subscript. So there's the sum, and this is actually pretty simple if you have the numbers. The arithmetic is elementary school arithmetic, so that's that. And we'll call that sum s sub n, and then that's in many cases all that you can do. But the last thing here, the last of the 4 s's, is that sometimes you take the limit as n goes to infinity of the s sub n's. But in a lot of applications you can't do that. There are some times when you can and when you should, but not always, so that's why I said sometimes. Okay, so that's the integration process. And when you look at the picture here, what you're seeing in, like, over this subdomain is the height defines a rectangle, and that rectangle is approximately the area under the curve over that piece of the domain. And when we add those up, we get the area under the curve. So this is the first part of the area interpretation. And right now that only applies if the function is positive. So number 1, integral a to b f of x dx. And this is if f of x is greater than or equal to 0, is the area under the curve. This is actually very useful in computation sometimes, because if you have a nice graph of the function, you don't even have to have the values, but if you have a nice graph, you can approximate this area by counting grids, squares under the graph. And so that's the thing that people pretty commonly do. And so that appears in your homework as well. So you look at, and you've got some graph, and you have a grid. I'm just going to do this kind of lickety split. And then you count the squares. If you want to be really clever about it, the graph would be on graph paper or something, obviously. You might say, well, I got a half of one from here and a half of one from there, so there's one that adds up. But you're getting an approximation, so that's all fine. Okay. The problem is this only applies when the function is positive. So what happens when the function is negative? And so I'll put that, I'm going to do that in red because it's like losing money. If f of x is negative, what happens is you go through the same process. You subdivide, you sample. Now all the samples have negative values because here's the axis and the value of the function is negative. And then you form the sum. And what you're getting is the negative of the area. So if you have, oh, I screwed up the drawing, sorry. Here's y equals 0. Here's y equals f of x. And here's the sample. I'm not going to do the subdivision, just the sample. And so there's the, ignore this part. There's the x-axis. There's the graph. So there's our sample. The sample's negative. So you're going to take the negative of the height of this piece right here and all the way around. So instead of getting the area, you get the negative of the area. So if f of x is less than or equal to 0, then the integral from a to b f of x dx is the negative of the area. So that's an important fact. The next important fact, which ties right into this, so I'm going to go right into it, is that if you look at the integral from a to b of f of x dx plus the integral from b to c of f of x dx. So I've got two intervals that adjoin each other. That's the integral from a to c of f of x dx. And the picture here is pretty simple. So there's the graph of f. I happen to have drawn a positive one. And you go from a to b, and then you go from b to c. So when you subdivide this part, and you do the sums, and you subdivide this part and do the sums, well, basically you've subdivided this whole big thing and done the sums. And so you get the integral over the much bigger thing that's, formed as the union of the other two. So this tells you how to handle the situation where you're integrating a function that's partially positive and partially negative. So you split it at the roots and do the areas that way. When you're doing the integral, you just do the integral. But if you want to separate it out and look at the areas, and so what happens is this: if you're looking from a to b at some function and it crosses the x-axis, which I've put in red, x-axis. So it crosses that. Well, the parts that are above the integral is the area, so that gets counted positively in the integral. The parts that are below the integral is the negative of the area. So if you look at the area there, then you negate that to see what happens to the integral. And so this is the complete area interpretation of the integral. The parts above are counted positive. The area is counted positive. And the parts below the area, you have to negate the area in order to get the integral. The area is positive, but the integral is negative. So same absolute value, but so this is the sign of the contribution. Okay. So we've divided things this way. We've kind of divided things at the x-axis, and And so there's one last little fact about integrals that we can throw into this, and this comes up actually more than you might imagine. Um, the problem here is if we look at the integral from a to b, and we're given a and b symbolically somehow, we don't know which one is the bigger one unless we might have to do a lot of work, but we don't have to do the work to do the integral. So let me just make a note here that the integral from b to a of f of x dx. So you're confused, you don't know which came first. So that is the negative of the integral from a to b of f of x dx. So there's the statement. So this is pretty hard to read. You got to read this quite carefully. Here we have a certain order to the endpoints of the interval, and here we have the opposite order. So one order, opposite order, and that changes the sign. And the reason that changes the sign is it goes back to here, is if you get these out of order, then this becomes negative. So every term in the sum is negated, and so the whole sum is negated, and the limit is negated. So it's this right here that determines the sign. If b is bigger than a, this is positive. That's what we usually draw, but sometimes we don't know we're doing that. We have b is less than a, and that's what this little statement's all about. So those are fun facts about integrals. You can use them to, the big use is to look at areas and decide how to handle those as integrals, especially if you have a graph. On graph paper, you've got grid squares, and you count the grid squares, but the ones that are below the axis get counted negatively. So that's how we handle these things. And you can do an awful lot with integrals just by knowing these fun facts.